Today we're going to be looking at gas laws, two in particular, Boyles' law and Charles' law. We're going to try and create relationships, mathematical relationships, based upon how the molecules behave. The first one we're going to look at is Boyles' law. So what I'm going to do is we'd like to look at pressure and volume, and how does the pressure inside a container change as the volume changes. So my question to you is the pressure-volume graph linear? Okay, so what I'd like to look at is a virtual simulation. We have a syringe on the left-hand side connected to a pressure gauge. And what we're going to do is change the volume inside our container. So we'll take a few examples, maybe somewhere around 12, and then another sample around 15, and then maybe another sample around 18 or so. If we graph those on a pressure versus volume graph, we end up with a nice 3 dots kind of in a row. It looks fairly linear. But I don't know whether it's going to be straight or not. So maybe I kind of have lots of points in the center. I need some more points on each end. So let's go back and collect some more samples. So let's go way high. Let's go up to around 5. And let's go around 7. And let's get some 20 and maybe 24. 25, 27-ish, get one on the edge, and maybe one more right in there. Now if we graph those, we end up having a fairly nice curve, a nice asymptotic indirect graph. So what this means is this is going to gradually approach the x-axis but never touch. This is going to gradually approach the y-axis but never touch. It's called an asymptote. It's asymptotic. So if we retrace our graph that we just looked at, it might look something like this on our graph. There we go. And so from there, we can see that it's never going to touch the y-axis. We're going to never touch the x-axis. Why is that? How come that is? Well, suppose we start over in our right-hand container, and we put 4 or 5 molecules in there. They're going to be bouncing around, and as they bounce around inside, they're going to collide with the walls, and they're going to push on the walls. Well, that's great. As we decrease the volume, and we have the same 5 molecules in there, now they have the same number of collisions, but in a smaller space. Those collisions are more concentrated, they're more focused, and so they're going to push on the wall. They're working more together. They're going to push on the wall more carefully. And then we go to our smallest section on the right side, on the left side, sorry. Then we have those same molecules kind of compressed nice and tightly and pushing quite hard. We probably should investigate why this shape is the way it is. If we made this volume on the right-hand side infinitely large, a huge container, there's going to be a little bit of pressure. There's going to be some molecules pushing somewhat on each edge, and even if it's teeny, teeny, tiny, even if it's unmeasurable, there's going to be some pressure. So it's going to get to a small pressure. As my volume gets big, the pressure gets smaller, but there's always going to be some. As I change this, and I compress it more and more and more, there's going to come a point in time where the molecules are basically touching each other, and so you're always going to have some pressure. That pressure is going to get very high very quickly. Let's look at a microscopic view. So now we're going to enable this, and we can start our graph. As we decrease the volume, the same number of molecules have a smaller space to move around in. They collide more often with the walls. The collisions are more focused. But we've changed our volume quite drastically, and there's been a very small increase in the pressure, because the gas molecules are far apart. And so if you're asking them to squeeze a little bit together, well, it's not a very big deal for them to squeeze together because they're quite far apart as it was. However, now that we're getting quite tight, now small changes in the volume are going to make huge changes in the pressure. Until we finally get something like that. So now we have lots of molecules colliding with the container at the same time, and so we have quite a high pressure. Okay, The instructor should press start on the CENTEOS and answer the following. Students, could you please answer the following question? What happens to the concentration of the collisions as the volume decreases? A, the collisions increase in concentration. B, the collisions decrease in concentration. C, the collisions happen harder. D, the collisions happen weaker. E, nothing changes. Please press pause on the video. Okay, so it's kind of a little bit of a trick question because we want to know what the concentration of the collisions are. I agree that it may be confusing to answer collisions happen harder as you decrease the volume, answer C, but that doesn't answer the question. The question was, what happens to the concentration of the collisions? And the concentration increases, A. Okay, so Boyles derivation. Here's our nice looking graph, our pressure volume graph. And we're going to derive a formula. This kind of process is going to be valuable to us in other situations. So not only do we need to worry about the final answer, we need to worry about the process. Let's try a couple things. Here we have our pressure volume graph. Suppose we were to pick one point, perhaps down on the right-hand side here. We have a relatively small y value, and we have quite a large x value. And so together we could multiply them and get a number. Suppose that number turned out to be 200 for our first point. Well, here's an interesting thing. Suppose we were to pick a different point, perhaps higher up. Perhaps we pick something that's high on the y-axis. Well, that means our y-axis value would be quite large, our x-axis value would be quite small. If we multiply those two numbers together, it turns out that you get exactly the same number, 200. And we'll call that K2. Now, that 200 value is not important. I just made that up. I don't know what the number really is. It changes for different gases. The number 200 doesn't really matter. The important part is, it doesn't matter what 2 points I pick along my graph. When I multiply the x and the y together, I always get the same constant number. So we're going to call it k. And what that means is, if we start off with k1, our bottom point, it's always going to be the same as k2. It doesn't matter what points I use on this graph. When I multiply the x-axis by the y-axis, I always get the same number k. Well, k is pressure times volume. And we have some 1s and 2s in theirs. And so you end up with the formula P1V1 is equal to P2V2. This is known as Boyles' law. So I can use this equation if I knew 3 of the 4 things to find the missing one. So perhaps I'll change a volume and a pressure, and I can measure what the new situation might look like. Let's try an example. In a 5-liter container has a pressure of 3 atmospheres. Calculate the new pressure if the same gas is compressed to 2 liters. So what I would do is I would use P1V1 is equal to P2V2. I would substitute my units in. I have to make sure that the units are the same for each one. So if I'm going to deal with atmospheres in this question, I have to be consistent and always use atmospheres. Likewise for liters. So I have 3 liters for my P1, I have 3 atmospheres for my P1, 5 liters for my volume, and 2 liters for my V2. I do a little bit of rearranging. 3 times 5 divided by 2 gives me 7.5 atmospheres for my final pressure. Now we'll look at Charles' law. Now, Charles' law looks at something very similar, except instead of looking at pressure and volume, it looks at volume and temperature. So without knowing it very much right now, I'm going to ask you to predict for me. What's going to happen to the volume of a container if I change the temperature? What will the graph look like? Will it be A, a downward slope, B, an inverse slope, C, an upward slope, or D, straight across?